start.
Okay, hi everybody. It's 10:30, so let's begin with the session. Sorry, 9:30. My clock is set to Amsterdam time still. Hello everybody. This is the Quantum Internet Research Group meeting. We're going to have a session for 2 hours. I'm going to go briefly over the chair slides before handing over to our speakers. As a reminder, the session is being recorded, and I'm first going to go quietly over the note as a reminder for everybody. I'm going to the note now. And as usual, a reminder, we are an IETF group, and so therefore our focus is on research and research collaborations and not standards development. And with that, also another reminder that the session is being recorded. For those who haven't signed in, please sign in using the QR code. And remember, if you want to join the mic queue, to use the there's a tool in the app or the browser where you can join the queue, so that the online and in-person queues can be handled. Some tips for how to find it through the agenda, through the IETF agenda website. There's an on-site tool in the chat room, or you can just use the QR code, which has disappeared. Or it's actually on the mics, so you can also use the QR code. And with that, let's begin the actual meeting. So welcome everybody. We're at the Quantum Internet Research Group meeting at IETF 121. Today, our agenda is fairly busy, but also quite interesting. We're going to focus today on 4 interesting talks, and also a pretty brief presentation from Diego with an update on his draft. So we're going to start with the update on the draft, and then go through talks. One from Marcello on quantum engineering, quantum connectivity. One from Piotr from Poland on the Euro QCI infrastructure deployment operational experience. So that one's going to be about the actual operations more than other things. And then we also have 2 speakers from the States, and ESNet and Berkeley. Inder and Wenji are going to talk about QuantNet. Document status current, as we already have 2 informational RFCs out of the door. Actually, one of them was finally published in between the last in-person meeting and this meeting. Yay. RFC 9583. So well done to the authors and everybody else who provided feedback. And the current ongoing draft is a multi-plane architecture proposal for the quantum internet. So if you haven't had a look at it, please have a look and provide your feedback. I'm sure it will be appreciated. And with that, my chair slides are done. And unless there's anything to add from you, Rodney, we'll jump into the speakers. Okay. Marcello, you're first.
Diego's up first.
Oh, sorry. Yeah, sorry. No, apologies, Marcello. Diego's first with his update.
I thought that was going to be the last one. Just scrap.
Slides are.
Yeah. Okay. Yeah.
Okay. Perfect. So I'll ask you to.
Do the next.
Yeah.
one,
Well,
yeah.
this is should be a very short one, because it's a draft in which we started working some time ago, but for the different circumstances, we were not able to update as in depth as we would like. Can you move on? The idea is that it's an idea that we have used in we were maturing in the past. It's about having a reference framework. It's not an architecture per se, but it's a framework in which we can reason about the different architectures and the protocols, and we can evaluate them. So it's not that we are mandating, or we believe that things are mature enough to identify a set of protocols or a set of layers, etc. But it's a way of playing with the idea of the different ideas that we have, and have a common reference that allows us to analyze the different proposals and even think about how to combine them, etc. And with having in mind that thinking that the quantum internet is going to be something separated from the current internet is, well, not precisely realistic. And even as Stephanie Werner said once, it's even not desirable. And the idea is how we can make an internet with quantum capabilities. For that, what we have tried to do is to leverage an RFC that was published some time ago on a conceptual architecture related to SDN, which is what they call class. And the idea is to adapt this architecture to the quantum environment. This is described there. I'm not going to go into more detail. Can you move on, Wojtek? The draft structure, as I say, it's about, as you see here, is about the technology foundations. One of the foundations is that right now we are having or gaining some operational experience with current QKD deployments. There are environments in which we are using, and well, we are going to have a presentation of the EuroQCA, etc., making the architectural proposals and some closing matters. The only thing new from the previous version, this is version 02, from version 01, is that we have added this idea of applying network virtualization principles, as is what we will see on the next slide. That is about the idea that we have started to work with a group in one university in Madrid, and we are talking with other research groups, in particular in Germany, and in the where is the other people working? No, and two units in two research units in Germany, and we are trying to use an environment that we call it a synthetic environment. It's based on a quantum simulator, and the idea is that we are trying to enhance it to allow us to experiment with different combinations of protocols, validating the framework, etc. And something that is important is what we want is to try to make something that is an integration with classical networks on the one hand, and mixing as much real stuff as we can, mix with emulated environments that allow us to say what would happen if we have 100 nodes. Because right now, the real deployments, they're going to account the costs and all the conditions is something that it would be complicated, and we want to get some insight about what would be the implications and the implications in the coordination with the classical networks. Well, we are executing the first experiments. One of the things during this hackathon on the weekend, where we had scheduled a meeting with some of the other people interested. Regrettably, I could not come, so we have another meeting next week to start coordinating on this. And the point is that we plan to add additional material to the paper itself. But well, we are pending the publication of a paper, and the academic co-authors decided that it was wiser to wait till the paper is published. And well, we have a list of things to be discussed regarding what we refer why quantum forwarding, making an analysis of the existing, and there are papers, and Marcello is going to mention in his presentation several of these proposals, mapping these proposals on the architecture, and we'll address some recent comments from our most appreciated chair that we received this week. It was, yes. So there we will introduce it. And so stay tuned, because when we meet in Bangkok, probably there will be a 03 version, much more detailed. And that's all.
Thanks, Diego. Let's defer questions to the end of the session if we have anything. So
there is actually a question.
Right now. Sorry, there actually is one question now. Okay, Tim.
Hi, Tim Chown. So I work for the UK NREN, the National Research and Education Network. It's likely at some point we'll be deploying this kind of technology. What's not clear from this, and maybe it's somewhere else in the working group, research group, is the sort of guidance from an operational point of view to an NREN or an ISP, I suppose, provider, in terms of what the key differences are between deploying the classic and the quantum internet, how we would operate it, given the types of fiber we have, the way we lease fiber, the way we get other connectivity, the way we operate and manage it. Is there something in this group that's looking at that? Or is
Well,
that in this? Or?
the idea is to derive from these experiments to derive some guidance. There are some documents that were generated when planning the EuroQCI on this, but they are very general guidance. It's about principles that are quite general in terms of use SDN, use software-based control, apply certain general principles for network management. Take into account always, do not forget that you depend on fibers, physical fibers that has to be managed. Detail, I would say that this is one of our goals here is to learn that at a minimum scale. I mean, not to say, well, I have 2 nodes. Right now we are running in Madrid, for example, a square that is, we have 4 nodes connected to fiber. You get some experience with that, but it's 4 nodes. It's very far away from a real network.
Can we in order to stay on time, can we move the rest of this to the discussion at the end of the session?
Yeah, thanks, Diego. And also, there is actually a talk from Piotr later that will actually answer some of these questions, I hope. Okay. Close deck. And now it's Marcello. I'm going to set you a timer for 25 minutes, Marcello, but you split the time however you want between questions and...
Can you see the screen?
Yes, we can.
Okay. I cannot see you, but okay. I'm not gonna see. Let's see. Okay. So last time we present something in the direction of quantum internet protocol, and this presentation goes in the same direction. So main focus of our research group is the protocol stack for the quantum internet. And to design a protocol stack, we need to understand which are the main differences between classical and quantum networking. So we are having a parallel of different activities, and here we are trying to organize what's going on in our research with a sort of stack like vision. So we are investigating entanglement generation, distribution, and utilization. And quantum connectivity goes in, at least from our perspective, in the direction of utilizing entanglement once has been distributed. We somehow, the community is convinced that entanglement is the resource and entanglement is different from quantum information, from classical information. So what we think is that entanglement is not the same, sharing entanglement is not the same way as transmitting qubits. And once we understand that there is this intrinsic difference between entanglement and quantum information, we think that this difference maps into different aspects. We call it open issues in the sense that these are the aspects that requires an effort so that this classical and quantum network can interact. And in this presentation, we are around here, around the fact that entanglement rules connectivity. And well, in the sense that classical connectivity is ruled by physical proximity among nodes, whereas quantum connectivity is ruled by entanglement. And in this perspective, we have somehow found out 3 main differences between physical connectivity, or the connectivity where we are used to have in a classical network, and quantum connectivity. So the connectivity is time variant because entanglement can be used and wasted. Then the connectivity is independent from the physical node location, meaning that once you have an entanglement with a faraway node, you are somehow connected with that node. And this is something that it's really becoming mainstream in the research community. You don't have only bipartite entanglement, but you have multipartite entanglement as well. And once you have multi-party entanglement, which of course is very hard to generate from a physical perspective, you can choose to have on-demand connectivity. You can change the connectivity on the fly. You can adapt the connectivity of your network to the demands of your network on the fly. So instead of having, in case of 4 nodes, 6 EPR pairs in order to have a one-to-one connectivity among any node, you can have less qubits, but having these qubits entangled in a higher state. And then once you have this, you can choose on the fly which pair of nodes or even which subset of nodes we define it as a quantum LAN can be entangled. And I will try to go as further as possible, as faster as possible. So this is our vision. We have multiple quantum LANs interconnected in an overall quantum network, and we have 2 main tasks: handling the connectivity within the quantum LAN, so in a single QLAN, and handling the connectivity among different QLANs. In a single QLAN, what we are envisioning is that entanglement is very hard to generate, so we will have dedicated hardware for generating and distributing entanglement. And this maps well with having an orchestrator, which somehow handle the generation and the distribution of the entanglement in a single QLAN. Of course, this is a huge departure from the typical LAN assumptions, because LAN, after all, is about Ethernet, and the design about Ethernet was to having a distributed network with no centralized communication infrastructure. And there was valid reasons back in the 70s to have Ethernet as distributed network. But we think that we somehow should challenge some of this assumption, and from our perspective, it makes sense to have a centralized architecture. So we have this node which we call orchestrator, which maps very well with the current hardware that we have in most of the labs in the world. And this orchestrator will distribute qubits among the nodes. And then we think that EPRs are one of the possible ingredients, but we may have larger states. And for us, the easiest state to work with is the graph states, because graph states can be very easily managed and represented and understood from people with the graph network or graph theory background. And the funny things about graph states is that there is this mapping between operation on a graph and Pauli measurements on the qubits of the multiparted entangled state. Why this is important? Because Pauli measurements from a quantum communication perspective are free resources. It means that we can manipulate the graph without paying in further quantum communication, but simply by operating with single qubits, by performing single qubit operations and measurements, which from our perspective are free resources. And once we distribute a graph state, we can manipulate this graph state. We started for a graph state which can be implemented in reality. So linear graph states with current experiments have produced linear graph states in photonic technology up to those qubits. And starting from this input, linear graph state produced at the orchestrator, we start manipulating the graph, the topology defined by the graph state. And we find out that almost all the 3 main topologies known in classical network, bus, ring, and star, can be obtained starting from this initial topology. And what we call it as entanglement rolling is the possibility to manipulate this graph state so that we have a higher connectivity with respect to the original graph state. And this, of course, is something that is not possible in classical networks. And these functionalities requires a whole set of protocols that must be designed and implemented so that we can perform these functionalities. But this was within a quantum LAN. But when we want to extend connectivity among different QLANs, we need to make further assumption, as our main assumption was that only the orchestrators of each QLAN are somehow interconnected. So we have these longer links interconnecting different QLANs. And usually when you want to have EPR among nodes that are not directly connected, what you do is the classical swapping and purification. There are different families or generation of quantum repeaters, but overall, the basic idea is to have an EPR about remote nodes and to map this in a flow of EPR that moves from one node to the other. But if we go back to the graph states and we start manipulating the graph, what we can have is that by using a single APR between different orchestrators, so by using only one APR on the longer range, we can implement and obtain 4 communication archetypes. So for example, one archetype is that the peer or the clients of a quantum LAN becomes entangled with the orchestrator of a different QLAN, and we call it, for example, hierarchical peer-to-peer, when the orchestrator of a QLAN and the clients of the other QLAN are in a one-to-all connection, or client handover, when we switch all the clients from one QLAN to become client of a different QLAN. And these are the first 2 communication archetypes. Then we might also, again, with just one APR among remote QLANs, having a genuine peer-to-peer when one client of a QLAN join all the other clients of the other QLAN in a one-to-all network. And finally, role delegation, which is essentially when a client of the first QLAN become orchestrator for the other clients, for all the clients of the other QLAN. Of course, the amount of entanglement shared between QLANs cannot be enhanced by local operation classical communication, so by our manipulation of the quantum LAN. So there will, at the end, there will be just one APR connecting the different QLAN, but what you can achieve is to have this APR shared by different subset of nodes. So what we were trying to investigate was, and I will conclude, that the topology that we can have in quantum networks can be manipulated with just local operation and classical communication. And summary is that the concept of neighborhood, which is one of the pillar concepts in routing, for example, any routing protocol depends on a concept of neighborhood. It's up to you. You may engineer your neighborhood to obtain any connectivity that you want. And of course, we have still open issues to investigate, like the amount of classical communications that we have to pay, because after all, we are performing local operation and classical communications. The trade-off between initial resource and final connectivity. And also the relation between the initial physical connectivity, meaning the fibers network that we are assuming that we have in the original network, in the original physical topology, and the artificial connectivity that we can achieve. But still, what we are trying to stress with this series of presentations is that we need somehow to departure from trying to map quantum networks into the classical TCP/IP protocol stack. And we should also take this period or this moment of research as a way to challenge the assumption of classical TCP/IP, because after all, we are just starting to investigate these marvels of quantum information. There is so much to be done. And I think that I will stay in my 15 minutes that I was expecting to use.
All right. Thank you, Marcello. So you're actually finished well ahead of time. I think we're in pretty good shape. So questions? I don't see anyone in the queue yet. Give us just a minute here for people to jump up with questions. Inder is coming to the mic. Inder, are you logged into the?
He is logged in.
I think I was logged into Meet. Echo.
Yes, he is.
So yeah,
No, just kind
go on, but raise your hand next time.
Okay, next time. So Marcelo, I had asked for the graph states. I mean, it's a quantum process. In terms of a protocol or standardization, what information needs to be conveyed classically in order for the graph state, to be established? Is that clear, or is that mostly all happening in the physical layer, the setting up of the graph states?
No, actually, that was one of the. Let me go back here. So, for example, the issue, the trade-off that I was mentioning in this slide, right? Three open issues in terms of classical communication. Once you create entanglement among remote nodes and you start manipulating that entanglement, you have classical communications that exceed the boundary of your network. So you cannot think that classical signaling will be limited to within the network. You need to have a classical routing protocol in place. You need to have inter-network forwarding, if I got your question. So we started, we just submit a conference paper with a quant about network simulation or graph states manipulation and simulating graph state manipulation, where we start defining the message, the classical message, and this classical message needs to be forwarded far away of your network.
Inder says thank you. So I forgot at the beginning when we were doing administrivia at the front to thank Dave Oran for doing the note taking for this. But a 2-hour meeting with one person with one note taker can be a little onerous. So if anybody wants to jump into the note taking and give Dave a hand, I'm sure he would appreciate it. Let's see, Tim is in the queue, and then Diego. We'll follow the order in which you guys, showed up in the queue.
Great, thank you. Tim Jones. So yeah, that was really interesting to see the way you sort of broke it down and listed the areas there. Coming back to I think it comes back to the question I asked earlier, which is where in this is like the protocol side and how it all works, but the sort of operations and management side of it, is there people looking at that and how from a operator point of view, you're going to manage and operate this quantum internet, these quantum connections, etc.?
Well, so again, the question is about the classical signaling needed for handle these operations, right?
Possibly, yeah.
Okay.
Yeah, that's the open question. What is it going to look like? Is it going to look classical? Is it something else?
Well, you have definitely, whenever you have local operation and classical communications, you need to have these qubits to exchange classical information. You need to have a signaling for that. So in the lab, what we are trying to do in the lab in terms of experiments is to start defining this classical signaling protocol. Okay, just to give you a hint, whenever we have our source that start to generate entanglement, we need to have the source exchanging information with the detectors, because we need to have the training session completed before start taking actual measurement. Okay, and of course you need to define a new protocol which a new classical protocol which will either use TCP or UDP. So that's the classical signaling. And in the lab, when you're doing actual experiments, you have to design everything from scratch. And most of the lab doing research on quantum networks are reinventing the wheel. So somehow we have more or less the same needed. For example, temporal synchronization. And most of the people in the lab doesn't have a network background. So they don't even know that there already exist protocols for solving those problems.
Right.
Just to give you an example, there is this, what was the name of the fine synchronization, the synchronization protocol? I'm assuming that Diego used the CERN synchronization protocol, White Rabbit. Yeah, White Rabbit is a CERN synchronization protocol for slower than nanoseconds synchronization. Okay.
Yeah.
Most of the lab are not using that protocol because the background of the people doing experiments lack of the expertise.
Okay.
And what we think is that having the network community aware and involved in these quantum network experiments may open collaborations so that we don't reinvent every time the wheel, but we start using the right tools that we already have in the classical networks also for managing the quantum network.
That sounds good. Thank you.
Diego.
Yeah, no, well, that's precisely what we're trying to achieve with this framework architecture. It was interesting. Is precisely this defining a playground for bringing together, you quantum heads and us network heads and try to. There is regarding with this and well, according to my understanding is that even when you're talking about distributing entanglement, the entangled states, you need to identify them. I mean, to make some sense at the end, each one of them, and that implies addressing. I mean, at the end, is a form of addressing. Taking into account as well that whatever we think about routing, about packaging, not building packets, but packaging somehow the information, etc., has to do with these addresses. Do you have any idea or anything in mind about how to address these states?
Okay.
How a quantum address would look like?
So in the last meeting, we present the scratches or ideas, and the overall feeling is that okay, let's put it this way: we are investigating this, and we hope that we will present something more concrete about quantum internet addressing in the next IETF or IETF meeting. But the issue, at least from our perspective, is that if you want to challenge classical hierarchical addressing, you need to find a use case where you can show some advantages. And this is what we are doing right now. And for us, the manipulation of the connectivity will maps with the advantages of having a quantum internet addressing. So if you want a short answer, yes, I think that we should move to quantum internet addressing, but to convince the audience that is in your room, we need to find a use case where we can convince even classical networks that challenging the most fundamental principle of current classical protocol stack is worthwhile to be investigated. Thanks,
One more question from Roland, and we'll do this the last one for this talk.
Yeah, very quick question, Roland plus KIT. I have no experience with the quantum side in that sense. So multipartite entanglement, isn't that more fragile than the, let's say, simpler bipartite entanglement?
I think that it define fragile. Everything is fragile in the quantum domain.
Yeah, sure.
What you can do, and actually one of the first paper proving theoretical this was from Whitek group, from Stephanie Wenner group, is the following. You can assume that you create multipartite entanglement within a single node, okay? Actually, every day, whatever the people that are using quantum chips from IBM, they are generating multi-party entanglement, because any quantum algorithm requires multi-party entanglement to have any kind of advantage over the classical counterpart. So you may create multi-party entanglement in a central node. Then you create EPRs, so symbol bipartite entanglement among nodes, and then you teleport your multi-party entanglement to the remote nodes.
Okay, got it. Oh,
I didn't. So just actually the challenging part from the experimental perspective is not generating multi-party entanglement, but is converting multi-party entanglement generated within a chip, so at a microwave wavelength, to optical wavelength. That's the challenging part, transduction, not generation of entanglement.
okay, thanks.
Great. Thank you, Marcello. And thanks everybody for all the questions and interesting discussion. We'll move on now to the next talk. Piotr, are you online? Are you able to share slides or share your screen? Piotr, yeah, I can see.
Yeah, you should hear me. No.
Yes, we can hear you. Do you want to share your slides using the built-in system, or do you want to share your screen?
Yeah, let me try to share.
Okay. Oh.
Whoops, we both clicked it. Sorry. request again, please.
Okay.
Yeah, double switch.
You're approved now.
Okay, let's see. It's not showing up yet.
Oh, it's here.
There we go. All right.
Okay. You should see my presentation at the moment.
We see that PowerPoint. Yeah, we see your presentation. Piotr, I'm going to give you 25 minutes. It's up to you how you split it between your presentation and questions. You should see the timer on the Meet Echo screen. So go ahead. It's your floor is yours now.
Yeah. Yes. Thank you, Wojtek Groth, for giving the opportunity to present few elements. I think it will fit with the questions and the previous presentation. So what I wanted to present and show are some basic experience and thoughts after the initial deployment of the QKD QCI network that we did this year, and the experience from one of the links that we have already for almost 2 years, since 2022. Not only from the QKD point of view, but a single photon device point of view. So just a few things for analysis and maybe future discussion. So few things, just a basic thing about us. So we are Polish NREN, so National Research and Education Network. So we run our backbone NREN network in Poland and also participate together with the colleagues from NREN Europe, NREN networks in Europe within the GIANT community. We have HPC center activities and everything connected with the new technologies in ICT, and also strongly over the last year, quantum communication and computing, connected also with optical sensing systems. So, but mainly from the use cases, deployments, practical scenarios, and training point of view. So not from the point of the pure hardware, less hardware, I would say. So we have two data centers and living lab, and as I mentioned, local network in Poland and the backbone network that we run in Poznań. But we are co-owner of the airport, which is near Poznań, what we use for optical sensing system, and also quantum communication, especially for satellite connectivity that we plan to do using this facility. So now regarding the activities, as a short introduction to the EuroQCI network that we've managed to establish this year. So we are owner and operator of the NRAN network in Poland. So all the collocation sites, all the fibers, so the passive and active equipment, everything is owned and operated by us. So it gives us opportunity to have a full control and tune a lot of things that it might in other way be difficult with shared environment when you rent the infrastructure from pure telco operators. So it has some positive things. And as you can see, we have 5 HPC centers in Poland. So in Gdańsk, Poznań, Warsaw, Wrocław, and Kraków. And these are the main points and nodes that we've selected for the QCI network that we have, that we've established. So they are gathering the QKD use cases, the networking scenarios, and the connectivity access to the network that we have. A part of the activities, so we try to be active. We are part of the EuroQCI infrastructure, but also EuroQCS. So if everything will be fine, we will have till May, June next year the ion trap machine established under the EuroQCS, which will allow us to do, of course, not only computing experiments, but we also hope to be the ion trap system to be a part of the distributed quantum computing system. So you can do the ion photon entanglement for blind quantum computing, but it's future work. So it's very, very early stage. But going to the QCI network. So as I mentioned, we have main HPC centers that are interconnected by our QCI network. And this infrastructure, the QCI infrastructure that we've built this year, is based on our NRAN Pioneer network infrastructure, both in terms of the fiber infrastructure, but also in terms of the management that is needed for key management system and monitoring of the devices and all the systems that we need to support the QKD systems. And our network is, you can see the scheme of the network. So up to April this year, actually March this year, we've built 1,350 kilometers of intercity QKD links. And together with the link from Poznań to Warsaw, which is here in the middle, this was established 2 years ago and contributed to the project. So together with this link, we have 1,770 kilometers of the intercity links between the HPC centers that are center of the use cases, applications, and the and monitoring of the system. So you can see that it's star topology with backbone topology, but each site has also a connectivity to the local metro QKD systems that can be accessed for local QKD use cases and the applications that we can run over the systems. And based on the whole Pioneer network, we also constructed, actually, this was the biggest challenge that I will give you a few words later. The biggest challenge is that you need to build your separate network for the management and for the KMS services. And you need to properly assign the access control, the connectivity between the devices. So it is, I would say, it is a challenge. And this whole network is based on the dedicated fibers. So the quantum channel is, of course, transmitted is established over the dedicated dark fiber. And what is interesting is that on most of the links, it is established on a dispersion compensated fiber. So it's not classical G652, but G655 fiber. Why? Because it improves a little bit. From our observation, improves a little bit the alignment time for the quantum channel and the dispersion compensation that you need to have within the QKD system. And why the HPC centers? So the reason is that around the HPC centers, we've connected a lot of different labs, which are connected with cloud services, multi-scale simulation, reference time and frequency, smart campus. So it's a natural point, interconnection point for the potential use cases, not only for QKD, but in future applications for other applications that might be connected with quantum communication. So now I think Vicente already, Diego already mentioned about the testbed in Madrid, a few things. So I'm not going to deep detail to that, but using the infrastructure that we have, we also did a QKD and PQC integration. So basically we've emulated the satellite QKD links based on the hybrid PQC integration. But now to the points. So I think what is worth mentioning, our approach was actually gradual, increasing the complexity of the system. So we've started with metro QKD systems and metro links, and based on that, we've saw how the KMS system, how the quantum channel aligns, what's the short-term and long-term performance, what are the fiber cuts and the maintenance works which have the improvement, of course, the temperature, the seasonal fluctuations of the environmental conditions, how they contribute the links. So we started with the metro links. And then after that, we've established a long distance link between Poznan and Warsaw, which took it to another level in terms of the especially KMS configuration and working with the QKD equipment. So usually what I see from the telecom point of view, I think there is a still challenge in terms of, I would refer to the QKD equipment, but of course it may scale for general quantum communication systems also. That usually the devices are more tailored to the data center nodes and the larger colocation sites. Yeah, they are not so much tailored to the inline amplifiers, so regeneration sites that we as telco operators have. So, as you know, for the for the ILA sites, you usually have smaller racks. The temperature environmental control conditions are a little bit less controlled. It's not that tightly controlled, and you have different power supply delivery. So you not only have the AC but also DC supply. So what we did for our QCN network is that the QKD systems have the dual power supply. So one supply is the AC and the other one is DC, typical minus 48 volt DC supply. And the patch cords, of course, it's always for the quantum communication, as you probably know, it's crucial to have high quality connections. But what you also need is you need to secure the patch cord itself. What we've noticed that you have in some occasions where you have for the large time of the day also natural light, you can have the leakage of the outside light to the patch cord. So it's a good also to protect the system. And of course, you need to monitor environmental conditions, because if there are too high variations in the temperature, the time to cool down the detector in the QKD systems in the photon detector, it takes more time, and it's less stable, and the parameters are they need to be frequently recalibrated, or sometimes you lose the alignment of the quantum channel completely, and you need to do it from the beginning. So the next point, so in terms of the KMS, so what we did is that we have the KMS system installed on several devices as for the testing purposes, for laboratory connectivity, and for the operational purposes. You need, at least from my point of view, you need to have several key management systems, instances of the key management systems. To improve not only the performance, but of course, access on control. And then based on the KMS deployment, of course, you need to build the whole network that will allow the KMS to access your QKD devices. And this is a crucial point. This is actually the weakest point in the whole QCI, I think, Euro QCI at the moment. Maybe not deployment, but this is the most challenging part, because it's up to you as the telco operator to find a way how to securely connect your QKD devices, which have, of course, themselves, they have access control and all the secure connectivity conditions, but you need to find a way how to provide the KMS connectivity from your KMS system all the way down to the nodes and to your QKD devices. And this is a challenging part. And then the same way you need to, for your network operations center, you need to deploy the ability to monitor and log the data from the KMS system. Of course, the KMS system itself, it's not responsible from the functionality point of view for the monitoring of the QKD devices, but usually the vendors, they connect this functionality. So you have the KMS functionality, and at the same time, you can physically monitor the performance data of the QKD devices and log the data. So what we've did is we have a separate system for logging based on the Grafana services. And we have for logging all the performance and all the data for the QKD devices. So detection rates, key rates, quantum bit error rates, temperatures, and what I've learned that the QKD vendors, they provide a lot of data at the moment, and you need to spend a little bit of time to select the data that is really crucial for your point of view from the operator point of view. It's good that they provide a lot of data, but on the other hand, it may be too much for simple NOC services, because NOC, as you know, they don't, they need to react fast, they need to provide fast response and the update on the state, so they cannot go through all the detailed data. They need to have some simple statistics that they can refer to and give an update. And also the challenging part is the management of the certificates and the configuration for the QKD devices. So you need to store the certificates and all the profiles that you have for the configuration for the connectivity. And the KMS system, from the actual NOC operation point of view, it's hard to, I would say, it's not always ready for constant operation. So sometimes you need to log in multiple times to check some data. And in the NOC operation, you cannot wait for that. Yeah, you need to have fast access to the operations. You cannot repeat some features at all the same time. Also, one of the problems is this is particular for the QKD, is the management of initial shared keys that you need to have for your devices to start the QKD exchange. And it comes especially problem when you have long downtime on your link on the fiber maintenance. So as you know, the ISK is in certain situations is invalidated. So you need to set up again and validate your QPD link again. And from the operational point of view, you need to have a procedure for that and be ready to do it, especially when you don't have direct access to the system. And when you establish the link, it's usually the quantum channel alignment can be a long process, because you need to have at the beginning, you need to wait as the detector cools down in the system. You need to align the QKD protocol data, and then you need to wait for the secure key rate to actually provide the keys. You need few attempts to start the actual secure key exchange. So it takes time. So you need to take into account this from the operational point of view. And from the NOC operational point of view, I think the problem that you need to also address is to have access to the quick data regarding the status and the performance of the link, because you cannot discuss with the maintenance staff and the operators using the detection rates or the photon detection rates. That it's very helpful when you log into the statistics and see all the details, but it's too detailed and too complex to have a quick decision. So you need to have certain measures that quickly responds to the problem that you have. Usually in a typical classical system, you of course operate in the laser power and the power that you see on your devices. But in the case of quantum communication devices, of course, you don't have that. You can only discuss the detection rates, which give you an assess what's the performance of the channel. And also what I think is not discussed from the operational point of view well enough is the service channel for the quantum communication devices. As you know, for the quantum communication devices, we need to have classical channels also, for not only for synchronization, but for the exchange of the classical data. And it's true for the QKD devices, and it will be also true for the general quantum computing devices, quantum communication devices. And you need to find the best way how to embed and co-propagate this channel within your existing network. And in our case, on some links, we have a dedicated fiber for the classical channel for the QKD signals, but on some links we have a co-propagation, so the classical channel is embedded within the classical communication systems. And I think for the future, a wise thing is to treat the quantum communication channel and the links as a special kind of signals together, like with the reference time and frequency signals, because both of them, they have unique specification properties from the management and physical point of view. They need to have a precise monitoring. And as an example, I can show you here what's the influence in ILA sites if you have too much variation in the temperature. So you can see that on one of the links, the key rate in the QKD link varies quite heavily. And when you stabilize the temperature,
yeah. Just FYI, you have about 3.5 minutes, including Q&A.
Yeah, it's last slide. Yeah. So when you stabilize the temperature, you see that the key rate performance. But if the variation is too much, or it's not. Yeah. So that was my slide. So a few thoughts regarding the some practical things that I think. Of course, these are long topics, but I think it would be fine to share this. Yeah, so happy to take questions if you have.
All right, so we have about 3 minutes. So if there are any relatively quick questions, Tim Chong he put a comment into the chat already that he was impressed with us. Yes, I think Tim, you're up.
Hi, Tim.
Oh, sorry.
I know Piotr reasonably well from a previous project, but that was really good. So from an operational point of view, that's exactly what the sort of NOCs and the NRENs, the people working there will want to know. All those issues that come up when you come to deploy this. My question is, did you need to bring in any extra expertise for this? Whether your existing engineers, did they learn all this as they went? How did that go?
You need to pass a little bit of knowledge and to extend, but of course it's not possible to provide the whole knowledge. And the challenge also is from the EuroQCI point of view. As you probably know, the EuroQCI networks, you cannot share some details on the network, so you cannot give all the data to the maintenance staff and all the people. So you need to manage that also. Yeah.
Yeah, that was fantastic. Thank you.
All right, Wei, and sorry for getting you out of order there.
Okay, no problem. Wei Pan, thank you for sharing this. Actually, I'm new in this area, so I have a general question for the lessons you've learned, because what I feel is that maybe if the QKD devices can be integrated with the classical network devices, for example, if the QKD can be a module, can be plugged into the network devices, would that beneficial the telecom operators for establish and maintain the two networks together?
Exactly, Wei. This is the desired. The operators they look for that. So you have the QKD module, and ideally you co-propagate the quantum channel and the data together with the classical channel. But as you know now, there is a limitation in the distance, so you cannot do it over long distance links. You can do it over short links, but not long distance link. But it will certainly benefit if you connect this. You can integrate it together on a component level. It will help. And I just was last comment, and I think that the quantum channel and the QKD and the systems, they are very good sensors. If you co-propagate those signals together, you can correlate the different events on your network with the performance of the quantum channel. Of course, the quantum channel alone will not give you full the data, but if you correlate everything together using different techniques, like maybe machine learning, you can get a lot of interesting data. And there are also already works and papers regarding that.
Okay, thank you.
Thank you very much, Piotr. That was a very interesting talk, and it's great to see like actual experience entering the QIRG. So thank you very much, and
Yeah,
we can move
thanks.
on to the next speaker.
Yeah.
The next speaker is Inder. Inder Monga, please. Would you like us to share the slides and you tell us when to switch, or? Okay. Will you do that?
Sure. I try to use as less technology as possible. All right, just tell me when to advance.
Sure. So, hi, everyone. So this is my first time presenting at this group. Thank you for inviting us to present. So sharing a quantum networking project that is, we are building up, me and Wenji. Wenji is going to follow me, and we're going to build on each other's talks. So next slide. So there are many applications for quantum networking. What you heard from Piotr and from Diego was on quantum secure communications, or QKD. Our focus and our team's focus is on distributed quantum computing, on how to connect multiple quantum computers together. So far in quantum, we're just trying to connect two quantum computers together. Next one. Now, you might wonder, why is this the case? And if you kind of look at what is in popular press, is that the future of quantum computing is distributed. Scaling one node up is becoming harder and harder for people that are either developing superconducting qubits or putting a whole bunch of atoms together or ions together. And if you really want to get to error correction and the future of quantum computing to make a utility scale quantum computer, as I say it, many organizations are investigating distributed quantum computing. Now, distributed quantum computing does not mean building it across the continent, across wide area. It is quantum, putting multiple quantum computers in the same data center. It could be more regional or metro oriented as well, because there are some limitations. Sorry. So you can see a whole bunch of articles, and there are much more that I put on this slide. Next one. So just to kind of set the basics, why do we need quantum networking to connect multiple quantum computers up? So if you think of a quantum node, it's a computer node with a bunch of matter qubits. And matter qubits, again, could be a superconducting qubit, could be quantum dots, could be ions, could be neutral atoms. Now, you cannot transport them very easily. So the only way you can transport that information or entanglement, as they say it, is by entangling a photon with the matter qubit and moving the photon across a fiber or a free space channel. Now, if you really want to take it far, the equivalent in optical networks is EDF amplifiers. You put an amplifier in place, you amplify the signal. Those don't work for single photons. So what you have is the concept of a quantum repeater that can actually extend the distance between the quantum computers before you can entangle them. So I think most people in this room know it, but I just wanted to set kind of the basic assumptions here. So photon qubits are the ones that are what are called flying qubits, and the matter qubits are stationary. And the channel can be free space, optics. You can talk to a satellite using lasers, whatever it is. All of those channels work. Next slide. So how do you get, if you want to kind of take the layered architecture of the internet and try to apply it in the quantum space, and to kind of put these concepts that I talked together. So what you have is a notion of a physical layer. Now, the physical layer in this case is photons that are entangled with the matter qubits. Those, the BSM node is called Bell State Measurement Node. That is the intermediate portion that actually establishes the entanglement between the quantum node and another quantum node or a quantum repeater node, which could be in the middle. If you want to extend that across multiple links, the entanglement, what you do is a swapping operation at the quantum repeater node. This is a deterministic Bell state measurement. The other Bell state measurement is a probabilistic Bell state measurement. So you do a deterministic Bell state measurement swapping, and that transfers the entanglement from end to end. Now, if you have a data qubit or some information or state that you want to get from one quantum computer to the other one, you use this end-to-end entanglement to do quantum teleportation, which teleports that information from one end to the other end. Now, why do you use the word teleportation? Most of the people in classical computing copy bits, and it's all the same. The reason why it is called teleportation is because the entanglement and the data qubit on the left-hand side is destroyed. It magically appears on the right-hand side. And that is why it is teleportation, because one side gets destroyed and it is recreated on the other side, the same state. It is unlike classical information, which could be stored in memory, copied, read, which is what store and forward routing is, which is information being stored and read and transmitted. Next slide. So with this basics, what we are building in the QuantNet project is a 3-node quantum computing testbed. 2 of the nodes are trapped ion quantum computers, and we are establishing, doing a distributed algorithm that can run across both of those. One of the nodes is at Berkeley Lab in building 66 up the hill. The fiber that we are using is pre-laid fiber before this project was even envisioned. So it is normal fiber that is used for classical communications. And it is going into Campbell Hall on UC Berkeley campus, which is a physics lab. And then we have in Corey Hall something called a color center, which is silicon-based centers that can generate photons at telecom frequencies. Now, the trapped ion nodes don't generate photons at telecom frequencies, so you have to do something called a quantum frequency conversion to get them to telecom frequencies so you can transmit it over longer distances. Next slide. So the three major areas of this research project is to build repeater-friendly quantum node technologies, which is a trapped ion quantum computer, and the color center-based single photon source, which is at telecom frequencies. We are trying to do hybrid entanglement. It is very much like people who have been in the beginning of the internet knew that there were so many protocols and you had to build a multi-protocol router to interact between these multiple protocols. So what we're trying to figure out is how do you take a photon generated from a color center node and entangle it with a photon generated from a trapped ion node, which are two different matter qubits. Most of the current experiments are between same to same. That is also what we're doing, but that is part of the research. The quantum frequency conversion, how do you do it efficiently? Because in the end, the rate matters. Our current projections are we can establish entanglement in this network at 100 baud. So it's kind of the early stage of communication. And then building a software and protocol stack that can be deployed across larger and larger networks, which is a quantum network control, which is going to be most of the conversation today. We are not going to be talking about other things that may not be of interest to this community here. So what are the quantum network components? If you start thinking of an architecture, so you have a quantum N nodes or Q nodes. Now, they should be capable of performing both classical and quantum functions. And an N node is essentially a quantum computer and a quantum networking function. So if you think of equivalence in the classical world, it is basically a computer with a NIC card. And that is what a quantum node is. Now, the way you will envision that in quantum terms is if you have a quantum computer with, say, 1,000 qubits, you will take 900 qubits for computing, you will take 100 of those qubits for communication and dedicate it for establishing entanglement with another computer. And if you have a distributed algorithm that can run across, you will use that entanglement of those 100 qubits to actually run a distributed algorithm. Now, the quantum repeater is nothing but a small quantum computer. And if you think of an equivalence in a router, it is essentially CPU and forwarding, but it doesn't do any of the the computing piece of things. But it is essentially qubits also that can be entangled, which is very similar to a quantum computer, but to extend it to a larger distance. Focus on extension rather than focus on computation. And it has functions to correct errors and mitigate loss, because I think that's when you go longer and longer distances. The Bell state measurement nodes is to establish this entanglement across a link, and this is a probabilistic process. And the quantum channels are fiber or free space, and you can have optical switches and other things to actually send different photons at different frequencies in different directions in order to establish what is kind of similar to WDM today in establishing multiple channels. Now, we expect all of this to be controlled with a logical control. That's the easiest way to do it. As we grow bigger and bigger networks, maybe this will become more distributed. We don't know that yet. Next. So I'm going to talk a little bit about the physical layer. I know that is not of concern to most of the IETF participants, but I'm going to talk briefly on the physical layer and then move on to the other layers. Next slide. So the physical layer essentially is ions that are trapped, and what you do is you excite the ions with a laser and these are the different levels. As you excite the electron and it falls down to a different state, it releases a photon which is entangled with it. And the frequency of the photon is determined by, which level did you excite it to and which level did it fall back on. And collecting those photons which are entangled and sending it using fiber is what kind of the basic physical layer is. Next. This is what it actually looks like right now. I know this is not something that you'll deploy in a data center, but that is what it looks like right now. Next. And then the quantum frequency conversion basically takes, at least in our case of calcium ions, takes the 854 nanometer photon and converts it into 1550. Now, this also is not fully efficient process right now. What we're targeting is greater than 60%. Current state of the art is around 30 to 40% efficiency. And what's important is not to introduce more noise and preserve the polarization state, because you're using polarization qubits in order to do the end-to-end entanglement. Next slide. And the Bell state measurement node, this is what it looks like. Again, not something ready to be deployed in a data center, but it is the one that is implementing the Bell state measurement to establish the entanglement in the middle of the node. Next slide. I'm going to skip this slide, talk about the color center later in interest of time. So let me talk about network components, the higher layers, and the opportunities for standardization. And I will go through each of the layers and propose some things here. In the end, we see opportunities for standardization, both in how an orchestration and a management plane interacts with the architecture we presented, and the protocols for actually establishing and maintaining entanglement and knowing when things decohere across the network. And again, this is a very simple 3-node picture, but I'm sure as we build more and more components, we can make it more complex structure here. Next. So from an orchestration and management plane perspective, what all needs to be standardized? So we need communication and control of each of the nodes. Should we use netconf or something like that? We need common models of interaction. So if one vendor builds one of the quantum nodes or another vendor builds a quantum node, what are the common models for configuration management and control of these devices? Whether it's a YAML model, a data model that needs to be standardized. Topology discovery, if you are deploying this, which node is up and available, as you add new nodes, you want it to be automatically discovered and added into the management system. Some idea of network-wide state maintenance, which node is up and running, which is down, I think, which is very simple. And then the end-to-end connection setup protocol. So if I'm going to set up a path or across the network and I want to do path computation, those kind of things will happen at the centralized control. And then you have to actually make sure that that path computation process gets executed and finalized in the network. So that is the kind of sort of things that need to be standardized. Now, a lot of it seems very similar to what you already have done in IETF for packet-based or classical communication protocols. This will be different, but and we can learn and see what elements, what configuration elements and the data elements are actually needed to make that happen. Next. So if you think of the data plane and not the control and management plane, so obviously you need synchronization across the network, and there may be some basic services that are needed in order to execute this process. There are some real-time protocols to control the hardware that I don't think is within the scope of standardization, because it may be very closely tied to the physical layer, the choice of qubit technology, and it may be vendor proprietary. And maybe the physical layer protocols are not IETF's concern at all, so I didn't really dwell too much on that. Next one. So if you think of the link layer, which is what is the layer between a quantum node and, in this case, a quantum repeater node, but could be another quantum node if there was no repeaters. It is the establishment and distribution of entanglement. So that is what the link layer looks like. Now, the link may disappear as the qubit decoheres, but that is not something we should concern about. It could be that we are establishing multiple link layers at the same time. But what is required for establishment of a link layer is a successful BSM and classical communication between the two nodes. And this classical communication needs to be standardized. So the BSM implementation may be vendor specific because it's physical layer, but the communication of a successful Bell state measurement, which establishes an entanglement, could be a standardized protocol that needs to be talked about in both ends. Next slide. So from a network layer perspective, it is about setting up and doing the swapping. So it provides the path calculation and the routing to aid the end-to-end entanglement. So it's about having enough information to decide a path, having enough information to decide free qubits. The exchange of topology, state, and path setup needs standardization, even though the path calculation algorithms could remain proprietary. Next. From a transport layer, it is setting up the end-to-end entanglement across the multiple quantum repeaters. Now, in this case, I think similar to TCP, you need state management at the two end nodes and know when that entanglement either decoheres or is consumed by the application for computing. So state management and routing at all the intermediate nodes may require standardization. I'm not 100% sure yet. This is where, as we develop this technology, we'll have a better sense whether this does require standardization or not. So you see, as I go up layers, I'm going from must to may, depending on the experience we have. Next. So from the application layer, it is similar to the socket layer. How do you actually consume that entanglement? It may require issues, may be a protocol issue, may not be a protocol issue. It's too early to tell because we haven't really executed a whole bunch of algorithms here yet to know how and what that API should look like. But that is also something that if people are doing research in this area, it would be good to know. Next. This is kind of just giving you a sort of quantum testbed design. This is how we have deployed. There are control channels, classical channels, multiple fibers. We have, I think, 3 pairs of fiber between these nodes for different use. And we have some real-time controllers, ARTIC nodes that actually sit with the quantum nodes, and that the controller and the quantum computer and the QFC all become one big quantum node. Now, I didn't talk about quantum memory. You can add that to the system and make it part of the quantum node. I don't think it needs to be a separate addressable device, so to speak. Next. So you can learn more. There are papers that we have published. There is an article in the physics world, so you can learn more about QuantNet going to the website. I did not go into a lot of technical details on establishing and building the physical layer. Next slide. And there are some links. That's it. Thank you. I hope I have some time for questions.
Yeah, we've got 7 minutes for questions, so please raise your hand in the queue and ask your questions.
While we're waiting for others to get in the queue here, as speaking as an individual here, I actually have a question. Sure. So you said you don't think IETF is necessarily the right place to standardize the physical layer. I would agree with that. Then the question is, where is? Given that most of the people in this room were kind of fans of the IETF process and other standards organizations are not as open.
So I'll use Ethernet as an example. IEEE standardizes the Ethernet physical layer, and IETF does everything over that. So I think maybe IEEE is the right space, but again, with quantum, it could be a separate quantum standards group that specifies a physical layer. I don't know what is the right answer here, Rod, but it is a question that we should definitely investigate and pursue. And maybe it is for something for the IAB to kind of, or the IRTF chair to think about as well, in terms of building collaborations. I know IETF builds collaborations with different standard bodies, and it could be a collaboration between IETF and another standard body.
Bjorn's in the queue.
Hello. When considering the quantum computing emergence and comparing it with emergence of computing at the early tube times, I recall the designs had maybe 5 tubes allocated for the 1-bit ALU for additions and logic, and maybe around 60 tubes which were necessary for the networking part for the address decoder. So how do you assess this setting? Is there some similarity to with respect to the challenge in quantum computing and quantum communication in comparison to this earlier times for the CPU design and computing design?
I think it's very similar because right now, some of the qubits which are part of this QPU or quantum processing unit will be reserved for communication. How many of that should be reserved? We don't know because we don't have fully developed models of how often will an application use this communication qubits. Now, whenever you use entanglement, it is consumed, so you have to establish entanglement again, and it's a continual process. So how many qubits should be used to do this, and how do you actually create different frequency conversions to be able to do them simultaneously, or do you do it in the time domain? like also used to have time-based protocols and time slots, which Sonnet STH was part of. Whether you use time-based or frequency-based parallelism is also something that is up for discussion as the technology evolves. So definitely, I feel all of those issues then will carry over now, but will change as technology evolves.
Craig.
Thanks. Craig Rodine. I'm no physics jock. So are these streams of photons or single photons? Like what?
They're streams of single photons.
Yeah. Okay. So what, like frequency, what, you know?
So right now we are sending, for this particular experiment, we're sending on 1550 only a stream of single photons that we collect. And then because it's a probabilistic Bell state measurement, sometimes the link is established. There is a 50% probability that entanglement is established and 50% probability it's not. So once it gets established, there is a classical communication which actually confirms that the entanglement was established. The collection and sending of those single photons that are entangled are happening all the time. So that's why you can't use regular EDFA like amplifiers, because EDFA amplifiers produce a whole bunch of photons that are actually sent. With single photons, you cannot amplify them.
So what's the rate of those single photons? How far apart in time or space are your individual photons coming out of the experimental setup you actually have?
We don't have a good measurement there yet. Based on theoretical calculations of the loss in fiber in the collection efficiency between the ion and the fiber, and so there is going to be loss at every stage. Based on those losses, we expect 100 entanglements a second established across this 5-kilometer link.
Okay, so but my question was what about your trial rate?
It's 10,000.
10,000 trials per second?
Yeah.
So 10 kilohertz trial rate. Okay.
That's what, but we haven't measured to verify that yet. That is still based on theoretical understanding of the setup.
I have one more question. Are you trialing any applications with this yet?
So we do intend to run a distributed computing application once this is all up and running.
Any specific computation, or is
just
that still...
a CNOT gate.
Okay.
Start simple.
Very good.
But at the IEEE Quantum in Montreal, there were a whole bunch of people that are actually building distributed quantum algorithms, and there are people who are doing compiler work are doing that. So I think I see a happy marriage happening on those efforts when we come there. Thank you very much.
All right, I think that's, unless there's anybody else in the queue? Nobody else? Inder has fled the stage. All right, that brings up Wenji, and thank everybody. Thank you all so far for staying on time. This is going to give us a good few minutes to actually run some discussion at the end of the session if we keep this up. All right.
Oh, just scoot over, just put it right there.
Share the screen, right?
Yeah, you have to go for prime screen share, I think. Yeah. And then I'll approve.
There you go, there you go. It's got it.
Oh, let me start timer. There you go.
Good morning, everybody. Welcome to this Quantum Internet Research Group meetings. I'm Wenji from the Lawrence Berkeley National Lab. The title of my talk is the control plane stack and the two-level scheduler with network layer and protocol being developed at the QuantumNet. And in the next 20 to 25 minutes, I will present the quantum network architecture and the product stack design and implementation. And we have conducted in the past 2 and 3 years. So before the talk start, and we acknowledge the contribution and the support from the quantum research teams, and quite a few people here. And Inder is the PI. So Here is today's agenda. First, I will give a simple introduction to the ContiNet project. Inder already gave the good talk, and so I can skip these sections. And then we talk about the ContiNet control basic needs, what the control plan, what do we need, and to develop the control plan. Then talk about the ContiNet control plan design and implementations, and finally conclude this talk. And here is the first talk about, give some backgrounds about the quantum computing and the networking. And here now is the quantum computing and the networking is a worldwide initiative. And here is a few picture I grabbed from the internet. And the central picture you will see, this is the 2023 and the global investment in the field of quantum computing and the networking. The major player is the US, China, and the Europe side. And here is you see the competition in this field is intense. And you go to the internet, you will see these kind of the news and the race to the quantum supremacy, and the race is on for the new internet. So the competition is pretty intense. And what is now I talk about what is the QuantumNet good for, and it's quantum internet and quantum network envisioned to provide new capabilities that are impossible using the classical networks. That's new capabilities and range from the cryptography and sensing metrology and the distributed quantum computings. So here is three applications, and you can see the first one is the QKD, and using the quantum mechanics to secure the quantum communications, communications. The second one is the sensing and metrology, and using the quantum network connect multiple and the sensor and the props, and using the entanglement and build up the super correlations between the sensor and the props to improve the measurement and the precision and the accuracies. The third one is the distributed quantum computing, and using network and to connect multiple smaller quantum computer to bigger one to solve more complex problems. And here is the QuantumNet project, and see there is the PI. And this is a 5 years research project. The total budget is the $40 million. And the Berkeley lab is the leading institution. Other research labs, including the UC Berkeley, Caltech, and the University of Innsbruck. The project has two major goals. The first goal in hardware, we build 3 nodes and a test bed, and to test the basic elements of the quantum computings, quantum repeaters, and the quantum hybrid systems based on the trapline technology and the color center technologies. And in software, we build up the quantum network architecture and the control planes, protocols, and the controls, etc. And here is the QuantumNet research teams. And here you see the Inder is the PI, and he has a dozen of years of network research experience and the system research experience. The next one is Hartmut from the UC Berkeley lab, and he's worked on the trapped ion technology. Third one is the Tracy Northup from the Innsbruck, and she is expert in the cavities and the trapped ions. Then the next is Thomas Schenkler and the Alp Sibahigel, and they work on color center technologies. Then the next is Maria and from the Caltech work on the quantum frequency conversions, and the Erhan work on the trapped ions and the neutral atoms, and I work on the control plane and architecture, and the Lavanya work on real-time controls. And here's other research team students and the postdoc. And this is the 3 main research areas, and Inder already talked about it, so I won't want to repeat it again. So currently I'm working on the quantum control planes and the architectures. For the control plane and the architectures, and there are 2 goals. And the first one is build a quantum network control plane to orchestrate and manage it, the underlying physical layer technologies. There are different type of physical layer technology like trapped ions, superconducting qubits, and then the next one, explore and what a quantum network control plane should looks like in the future. So to automate high rate and high fidelity entanglement generations in a cost efficient, reliable, and cost effective ways. So that's the two goals for the control plan work. Then we go to the fundamental, think about what a control plan needs, what's the basic needs, and when we design and implement a control plan. The first one is, and we support the high rate and fidelity entanglement generation, distribution, and in an efficient, reliable, and cost efficient way. So because that the entanglement is the fundamental building block of quantum network. So the key entanglement functions in the quantum network includes entanglement generation and entanglement swamping and entanglement distillations there, right? And so here is the quantum network. It's a simple quantum network. You will see the quantum nodes and the two quantum nodes and the quantum repeaters. And you will see these quantum network operations, entanglement operations, involves many in-network operations. For example, the in-network operations, we do the end-to-end.
Wenji, don't wander over there. Oh. You'll lose the online audio.
So that one you will do the entanglement swamping. Once you do the entanglement swamping, you will send the information to the two ends. So it involves a lot of in-network operations and also relies on the maintenance of the states inside network. So this is a fundamental difference from the classical TCP/IP network. And from classical TCP/IP network is the end-to-end principles. So for the TCP states, it's put at two ends, and the minimum amount of states is put in the network, and the network just do the forwarding. So that's a major difference from the classic network. So that's because this different and well designed could be different. The next one is, and the second goal is a schedule the synchronized operation in a distributed environment. And the key characteristic of entanglement function in a quantum network, and first, it typically involves the multiple quantum objects in a distributed environment, right? You have one operations including the multiple qubits and the multiple quantum objects. So in quantum objects in the near term, we call the noisy intermediate scale quantum errors, and the quantum objects are fragile and sensitive to noise. It has limited coherence time. Then you apply a set of operations to be executed on the quantum objects. You want to execute the operations and in a tightly synchronized manners, and before the decoherence destroyed the quantum informations. Because you have multiple objects and you want to synchronize as operations start at the same time in the synchronize, but in the distributed environment. So that's the second major requirement. The third one is in the quantum network, and you need to schedule the calibrations to be executed regularly. So a practical quantum network requires long coherence time, and need the high fidelity quantum gate operations and high fidelity quantum channels. And this to enable such a capabilities, and each quantum device and in quantum channels must be calibrated and monitored and in the periodical manners. The next requirement is support the real-time and control in a distributed environment. For quantum, the accurate control and manipulations and the quantum qubits, and you need to the real-time controls. For example, you control the trapped ion qubits, you need at the microseconds levels. And if you go to control the superconductor qubits, and you need to go to even the shorter and the nanoseconds and the levels. So control plane require tight timing controls and imposing the hard real time and control the constraint and the lowest level. That's so we need to impose the real-time controls at the lowest level. The final goals and the ability to for the control plane to discover the network resources and build and maintain the network topology and making routing decisions, etc. And this kind of for any network, these are routine functions, and any network control plane need to implement. So the challenge for this requirement is we need to develop the efficient, extensible, robust, and reliable control plane to provide these functions. So to address this, the basic needs, and here is the our design solutions. So for the first one is that we do the logical centralized controls, and the centralization of the control states and the logic in a logical centralized control plane will provide fast and more efficient entanglement functions. So this is to address the goal one. The second one is, and we do the TDMA-like scheduling to support the synchronized operation and in a distributed manners and distributed environment, and also allow the collaboration to be executed regularly. So I using the TDMA, but in there it says that the TDMA is probably not the right word. So the point is, and we want to, some time slot synchronizations and so allow the synchronized operations and also execute the regular operations. So this is to address the goal 2 and the goal 3 for the needs I just mentioned. The next one is for the real-time control in a distributed environment. And basically, we were using the time critical functions runs on dedicated and real-time control systems. And then dedicated the channel. We have dedicated channels for the real-time communications. This is addressed the goal 4 I mentioned earlier. Then for the last one is the open plugin framework to allow to inclusion of the new service and functions in the control plane. This is addressed the goal 5 mentioned earlier. And this is the QuantumNet control plane design. This QuantumNet model and architecture. So Inder already talked about this earlier, so I don't need to repeat it. So basically, we have the centralized control, and we have the quantum nodes, Q nodes, and we have quantum repeater, and we have the BSM node. And this is the layered quantum network architecture, and also Inder talked about it, so I don't want to repeat it. So, but the quantum physical layer, and then from the quantum link layer is for the heralded entanglement generation and heralded entanglement distillations. That's for the segment entanglement generations. Then you do the quantum network there, you do the entanglement routing and entanglement swamping to do the end-to-end entanglement generations. Then you have the transport layer to make sure the end-to-end can provide, the service can provide to the application layer. And the application layer is, and typically people talk about QKD, but the more useful application probably is the BCQ and the black quantum BBQ, the blind quantum computings. And this is the two-level control framework, and currently we are designing. You look at this diagram, and the top one is it's a quantum network server. It provided the network-wide non-real-time controls, and it's a centralized controller. Then we have a global TDMA-like scheduler to handle network-wide the non-real-time functions. It has topology discovery, monitoring, and link completions and monitors. Then at the node level, you see at the node level, we have the dedicated real-time control systems to do the network level controls. And each node use dedicated real-time control systems. In our project, we're using the RTIC systems to do the real-time controls. Then at each node, we have the TDMA-like scheduler handle non-real-time, node-wide real-time control for the qubits control, for the gate operations, and for the node operations. And this is the node-wide real-time control, and we have the RTIC and the dedicated systems to implement the Q nodes. And also we're using the RTIC system to implement the BSN node. And recently we're using the RTIC system to distribute both state measurement and build up the BSM node. And this is the two-level control framework, the scheduler. And we're using the TDMA like the operations. So the total durations of the quantum net time is divided into the fixed time intervals. And then we allocate the free time slots and schedule the specific function at the specific nodes to allocate the free time to support the synchronized operation and support the regular operations. And you see here is in the QIRG server, and we have global TDMA scheduler. Then at each node, and we have the local TDMA schedulers. So this is the operations to do the free time slot allocations. Once they do the free time slot allocations and push down to each node, and then the operation to start at the same times. So in this way, we support the synchronized operations. We support the calibrations and in a regular manner. And here we will give a example to show how we do the two-level schedulers and the control framework to support synchronized operations. Here you will see there's a topology, and in that topology, and we will have a centralized controller. Then we have 3 nodes and 2 quantum nodes and 1 BSM node. Then look at the figure 2. This is the how and the physical layer, the end-to-end entanglement between the Q node A and the Q node B. And in that node, we apply the laser to shoot apply the laser to the ions at each node. And once the ion shoot at once the laser shoot at the ions, you generate I photon entanglements. Then the photon go through the channels, go to the Bell state measurement. The 2 photons go to Bell state measurement, and once they do the entanglement swamping, and once they boom, and then they build up end-to-end entanglement between the 2 remote eye. And here is see how the control plane and support such operations. And you see the entanglement request goes to the quantum network server. Then quantum network server do the analysis and see, okay, this is an entanglement generation request between node A and node B. Then do the analysis, admit this request, then do the routings and choose the path from the Q node A to the Q node B and choose the path in the middle. Once they choose the path, they do they assign the function along the path and at Q node A and the Q node B and the BSN node. So what function we need to schedule? Once to schedule at each node. Once each node is a function is assigned, then we also assign the free time slot for each functions at each node at particular times, and we find the common allocated the common free time slots. Then once the time slots are located and pushed down to each local nodes, and then each local node and the schedules at then afterwards the function will be executed at specific times and then to do the entanglement generations. So this is how the control planes support the synchronized entanglement generations. Here is now how we using the two-level control framework. We implement an open plugin framework. So the framework for exploring a range of quantum network approaches, including the work reference implementations and within the modular using the modular extensible software platform. And we demonstrate the real code on real hardware, but also create a bridge to support simulations. So we support also the simulations and the real experiment, and create an opportunity for the quantum network community to involve together. So this software should be open source and will be open source and plugin framework. And here it's the conclusions, and this talk discussed the two-level control framework for quantum network within such a network, and the two-level scheduler implemented to support the TDMA like the scheduling and network-wide non-real-time control and the network-wide real-time control. And the two-level scheduler is currently be evaluated in the quantum testbed, and it will be released to the community upon the completions of internal test. So the two levels control framework and the scheduler are not only designed for the quantum project, and hopefully it can be extended and to support other type of quantum network. And here is a few links and for the further readings. So any questions?
Yeah, we have, thanks, Wenji. We have two people in the queue already. First, David, and then Diego.
So, Dave Oran, I have two sort of, I think, closely related questions. When you talk about a real-time scheduler, I'm trying to get a sense of the time frame. You're talking about nanosecond level, microsecond level, millisecond level?
It depends on what kind of underlying quantum technology you are working on.
But I mean, your real-time scheduler, I'm trying to figure out what kind of scheduling frequency it's running at. Is it running at microseconds, nanoseconds?
So what do you mean? The
Well, how big are the time slots? That's another way of answering
the time slot for us. The time slot now is at the 10 microseconds.
10
so the
microseconds.
time slots. But for the underlying controls,
no, I'm talking about your real-time scheduler, which is
scheduler.
all
We do the time slot allocations at the 10 microseconds
okay,
level.
so
and
basically you need clock synchronization of about an order of magnitude better than
yes,
that.
yeah, that's some course level synchronizations, and the White Rabbit, that's enough. But
Okay.
if you do the real-time control at the lowest level and using the RT controls, that's go to nanoseconds or sub-nanoseconds level.
Okay, then the related question is, what kind of latency measurement accuracy do you need on the physical links? I mean, temperature is going to change them by tens of nanoseconds or more. I mean, what do you have to actually build in an accurate model of the link latency in order to maintain the synchronization?
That part synchronization is depends on what you mean the synchronization. If you just talk about the synchronization,
Well, if you
at
say a time
slot
slot is, for receive is at this point in time, you want that time slot to be when the photons arrive, right? And
it's
if they're not
not.
arriving at the, at the boundary of the time slot, you're going to lose
we
synchronization.
actually we do the Bell state measurement. That part and can be at the sub nanoseconds level. We use the HOM model, HOM experiment, to figure out the HOM dip.
Right, but you have to do it when the photons arrive, right?
No. And we choose the HOM dip, and then we find they
okay.
arrive at simultaneously. So for our experiment, and the wave packet is at 20 microseconds level. So our experiment is fine. But for some experiment, it has to be the picoseconds level. So that one there's no.
Right, you can't use a control channel.
Yeah, you cannot use a control channel to do that. You have to use HOM to do the calibration.
Great, thank you. Yeah, I got the answer I wanted.
Yeah.
Diego.
Just a couple of reflections on this. This is only focused on the entanglement forwarding. I mean, the physical, because one of the things that we are trying to do is to consider the idea that on the one hand, for sure, you need to have this, but to have let's say, real networks and you have more nodes, you need first as well to establish the physical connection,
yes.
the classical ones.
Yes.
You're not, I mean, this controller would expose this MBI to a integrated controller or whatever that would take into account the need for the switch, the pure optical switching plus this, right?
Yeah, because currently we are focused on the layer 1, layer 2.
Yeah, exactly. On the link.
We make sure the entanglement generation, the entanglement setup. Once the entanglement is set up, and then at the high levels, application layers, we can use in the blind quantum computings and etc. And we have not reached that stage yet. We focus on the layer 1, layer 2, and
so it's about guaranteeing that point A and point B are
yes, and the segment layer, segment, yeah, and after.
And you mentioned MBI. What is
which one?
The northbound interface.
What interface?
Northbound interface.
Yes.
You mentioned it. You have any idea of what particular MBI you're going to use, or?
So for the northbound and the interfaces currently is, and we only work on the CNAT and the applications, and so that still is at the layer 1, layer 2. But the one you talking about at application level, like the
no, I'm talking about using the controller. The controller.
Up layer, yes.
But if can you move on back?
You talk about the between here.
I need my glasses.
Between here, right?
Yeah. On top of it, because in one of the diagrams you have an MBI box.
Yeah, that one is, and it's, I want entanglements, right? You have application, I need entanglements.
And you're playing with netconf, Yang models.
That part I not think about that part.
Sorry.
I work on the low levels, and I not work on that levels.
Okay.
Yeah, we have not gone that part. Yeah. But one thing is, and we talk about, actually, you talk about it, that's the something we think about is the quantum socket. Actually, Ronnie talked about that, the quantum socket that a long time ago. Because the reason that we think about the quantum sockets, the quantum socket is we provide the continuous and entanglement service. So that part, and because we are using the centralized control, right? It's not like distributed the sockets and you establish end to end. So we have some architecture we currently thinking about provide continuous entanglement service through the entanglement, so through the centralized controller. Then you have the two ends, and the two ends, that's not just the network part, and also your computing systems. The operating systems, and you set up all the things in the middles. Then you provide some sockets continuously, and to get the qubits, matter qubits, and the communication qubits, and you maintain the states and through the end nodes, through the centralized controller, and that part we will have some results. I mean, some of the publications on that part soon later.
No, that connects somehow with what I was asking Marcello before on the addressing. I mean, because at the end we're talking about the objects we are going to use for communication and for manipulating the communication. I mean, and we had to name them. And even we cannot probably using the term address is even too much focus on the classical approach. But we had to name them to identify them. Whether they are endpoints, they are sockets, as you say, a quantum socket, those objects is something that we have to decide and reason about them, because it's a way in which we could build routing and identifying the different communication, not links, the different communication channels, and refer to them and use them. That's simply that. I mean, I have seen here on addressing is going to be an interesting matter in general.
I think the most reasonable one is like something like sockets. Inside the sockets, you have the matter qubits, right? But because now the coherence time is short, so you from the naming the object side, you just name the sockets. And inside the matter qubits, and because the coherence time is so short, and you have this matter qubits, and then once it decoheres and replace and with another one. So once you access the sockets and you just have inside the socket, there's a queue of the matter qubits, and it's still incoherence. And then you choose that ones and.
No, it's interesting that you mentioned that there is going to be a queue of mother qubits, because this is something that, yeah. I mean, the point is that I think that we have to make converge. For example, I like very much the ideas that Marcello has shared about these graphs, and that the objects that you have to think about this is about the graphs that and the equivalence between graphs, and mapping this idea. Well, personally, I had to think about that.
I have a small addition to it's not really northbound interface, but when I used to work on the protocols, I was a big fan of trying to follow using Yang models and GNMI and using gRPC because they're modern and cool. Okay. And also that's what all modern people are trying to migrate to, I feel.
All right. We should wind up.
Yeah. We should close up.
Thank you, Wenji. Okay. Yeah, all right. So we've got about 90 seconds or so here before 11:30. Thank you all for attending our full 2-hour Quantum Internet Research Group meeting. I am committed to being in Bangkok in March, but we have not yet discussed, of course, any agenda for actually convening a QIRG meeting in Bangkok, but it's likely to happen. And as Diego noted in his short presentation, he has a draft, an O2 version of the draft. I put comments on the QIRG mailing list yesterday about that. Please do discuss it, and let's see if we can push that forward. And we look forward to seeing you all in Bangkok. Wojtek, anything else?
No, that's it.
Thank you all. Thanks to both the remote presenters and the people who came, and we'll see you all in Bangkok.